Hello students, welcome to the session. My name is S. Vanaja, lecturer in physics from Government Polytechnic, Nirmal. Today we will discuss about the semiconductors. In this, the intrinsic and extrinsic semiconductors will be discussed in this session. There are two types of extrinsic semiconductors. They are p-type semiconductor and n-type semiconductor. So first of all, what is the semiconductor? So we know that the properties of semiconductors lies between the insulators and the conductors, the resistivity, the conductivity. So all these properties are lies between the insulators and the conductors, the electrical properties like resistivity and conductivity. And at the room temperature, they have conductivity lower than conductors and higher than the insulators. So as the temperature increases, the conductivity will be changed, but at the room temperature, the conductivity is less than the conductors and higher than insulators. And if you observe the resistance or resistivity of the semiconductors, this will be decreases with increase in temperature. The increase in temperature. Therefore, they have the negative temperature coefficient of resistance. The conductivity decreases, the resistance decrease with the increase of temperature. So that's why we can say that the semiconductors have negative temperature coefficient of resistance. And the resistivity or conductivity changes when a small amount of substances are added to the semiconductor. The conductivity resistivity will be changed with respect to temperature. As the temperature increases, the conductivity may increases, and as the temperature increases, the resistivity decreases. In the same way, the resistivity conductivity will be changed by adding some substances like impurities to the pure form of semiconductors. So when some impurities are added to pure semiconductors, then the conductivity and resistivity will be changed. So these semiconductors are two types. Elemental semiconductors means the basic pure form of the semiconductors. They are germanium, silicon. Germanium and silicon. And there will be some compound semiconductors also, like gallium arsenic. So by combination of gallium and arsenic, the compound semiconductor will be formed. It is gallium arsenic is the compound semiconductor, and the elemental semiconductors are germanium and silicon. And these semiconductors may be classified by adding impurities to the pure form of semiconductors, and they are intrinsic and extrinsic semiconductor. Generally, it is classified into two types: intrinsic semiconductors and extrinsic semiconductors. Now, the intrinsic semiconductor. A semiconductor is an extremely pure form. It's known as intrinsic semiconductor. Means there is no presence of any impurities in the semiconductor. Then it will be called as the pure form of the semiconductor, and it is intrinsic semiconductor. And if you observe the conductivity at a low temperature such as absolute zero, that is 0 Kelvin, all the valency electrons are tightly held by the parent atoms, or tightly bound to the nucleus by the covalent bonds, and electrons can't move through the crystal. Suppose if we observe the germanium or silicon, the pure form of the semiconductor, it has 4 valency electrons in the outermost orbit. So these 4 electrons of one germanium atom will be formed covalent bond with the other atom and shares the covalent bond with the neighboring atom, as shown in this figure. You can see the center, the circle indicates that silicon or germanium crystal, and it has 4 valency electrons in the outermost orbit, and for the center silicon atom there are 4 neighboring atoms, 4 another silicon atoms, and these 4 valency electrons will be formed a covalent bond with the electrons of the neighboring silicon atom. Like that, the 4 valency electrons will be formed 4 covalent bonds with the nearest silicon atoms. And these electrons are very tightly held by the parent atoms by the covalent bonds with other atoms. And the electrons can't move through the crystal. Why? Because they are tightly bound in the covalent bond. So no free electrons will be available to conduct the electricity. So there is no free electron present in the semiconductor at 0 Kelvin. So that's why this semiconductor, the intrinsic semiconductor, will behave like a perfect insulator at 0 Kelvin. So it will be behave as the insulator at 0 Kelvin. And if you see the two-dimensional representation of this silicon crystal, so observe how the covalent bonds are formed by sharing the valency electrons. I already explained this. So at 0 Kelvin, all bonds are intact and no free electrons are available for correct conduction. So it will be a perfect insulator at 0 Kelvin. Now, how to increase the conductivity for intrinsic semiconductor? So it will be happen by the generation of electron hole pair. What is the electron hole pair? We know that at 0 Kelvin there is no free electron present, so it is an insulator. Now the temperature increases to the room temperature. Suppose the temperature increases to the room temperature. What will be the changes in the intrinsic semiconductor? So as the temperature increases, some covalent bonds will be breaked. If one covalent bond will be break, the 2 electrons in one covalent bonds there will be 2 electrons. So 2 electrons will be free. So electron becomes free to move throughout the crystal. And if one electron just move from his position, then there is a vacancy. So there is a vacancy at that position in the covalent bond. Suppose one covalent bond is break and one electron is moving freely in the crystal, then there is a vacancy present at the covalent bond. This vacancy is nothing but the absence of electron is treated as hole. The vacancy of electron is called hole. And when the free electron is produced, the hole is also produced simultaneously. Means when free electron will be produced as well as a hole also produced. Means these electron holes are produced in pairs at a time. So this is called as electron hole pair. One free electron is generated by increasing the temperature, as well as one vacancy of electron is generated, and that is called as hole. Means for every breaking of the covalent bond, there will be electron hole pair in the crystal. So the concentration of free electrons will always equal to the concentration of holes. The number of free electrons is equal to number of holes. So therefore, at the room temperature, they have some conductivity. Why? Because there are some free electrons in the crystal at the room temperature. Some electrons are produced, some covalent bonds will be broken, and electrons are generated, free electrons are generated, free holes are generated. Now if you observe the charge of the carriers, so electron, as we know, electron is a negatively charged particle, the hole is called a positively charged particle. So these electron and holes are called as free charge carriers. Free charge carriers. And the movement of the electron is always the opposite to the movement of the hole. So there will be movement of electrons, and as well as there will be the movement of holes in the crystal. So the total conductivity will be due to the movement of electrons as well as the movement of holes. Means there is a electron current and there is a hole current in the intrinsic semiconductor. To break a covalent bond in the crystal lattice, a certain amount of energy is required. Means how these covalent bond will break? As the temperature increases, the covalent bond is breaked. So to break the covalent bond, some energy is required. That energy is 0.72 electron volts for germanium, and it is 1.12 electron volts for silicon. So this is the energy required to break the covalent bond in the crystal lattice. And the holes remains in the valence band. The electrons lifts to conduction band to take part of conduction of current. As we know that the valence in the valence band, the electrons are jump into the conduction band, then only by crossing the forbidden gap the conductivity takes place. So as the electron shifted to conduction band, there is a vacancy of electron in the valence band, that is hole. So electrons are jump into the conduction band and holes remains in the valence band. The energy to lift the electron from the valence band to conduction band is 0.72 electron volts, and for germanium, and it is 1.12 electron volts for silicon. So this is the energy, or we can say that it is the energy to break the covalent bond, or it is the energy to lift the electron from valence band to conduction band. What is the value? It is 0.72 electron volts for germanium and 1.12 electron volts for silicon. Now the effect of temperature on conductivity of intrinsic semiconductor. How the conductivity will be changed? By changing the temperature of the intrinsic semiconductor. So generally the semiconductor that is the germanium or silicon acts like a perfect insulator at absolute zero temperature, as there is no free electrons present at 0 Kelvin. So conductivity is equal to 0. So as at the room temperature, means at 300 Kelvin, some electron hole pairs are generated due to thermal energy, and they have small conductivity at the room temperature. But as the temperature rises further, more electron hole pairs are produced. So as the temperature increasing here, the electron hole pairs are produced. And at very high temperatures, the concentration of charge carriers will be higher. So here the charge carriers are electrons and holes, and the concentration of these charge carriers will be higher. So the conductivity of intrinsic semiconductor increases with the temperature. That is, the resistivity decreases with increase in temperature. So therefore, the semiconductor has the negative temperature coefficient of resistance. So this is the effect of temperature on the conductivity of intrinsic semiconductor. Then we go for the extrinsic semiconductor. So what is the extrinsic semiconductor? The pure form of the semiconductor is the intrinsic semiconductor, and here the pure semiconductor have some conductivity at the room temperature. Therefore, they are not of much use. There is no much use for this intrinsic semiconductor. Why? Because conductivity is very low at the room temperature, so there is no use of it. But by adding some amount of impurity atoms to the pure semiconductor, we can change the conductivity or the characteristics of the semiconductor simply by adding some impurities to the pure semiconductor. This process of adding impurity to the pure semiconductor is called doping. Adding any amount of any impurities to the pure form, this process is called the doping process. Means due to doping process, the conductivity here increasing. To use in any electronic devices, we are using this extrinsic semiconductor, and we are going to increase the conductivity by just adding the impurities, means by doping process. So doping is done at a rate such that only one atom of impurity is added per 10 power 6 to 10 power 10 semiconductor atoms. It is very low concentration. For 10 power 6 of pure atoms, there is one impurity atom. This is the concentration of impurity in the extrinsic semiconductor. This is a doping process. Then doping rate. Only one atom of impurity added for 10 power 6 to 10 power 10 semiconductor atoms. And on adding impurities, either the number of electron or holes increases. The number of electrons and holes increases, and the doped semiconductor is called extrinsic semiconductor. So by adding the impurities, electrons or holes are increasing here, and the doped semiconductor is called extrinsic semiconductor. And by adding the different types of impurities to the pure form, there are two types of semiconductors. They are N-type semiconductor and P-type semiconductor. This is the classification of semiconductor by adding the impurities to the pure form of the semiconductor. By adding different types of impurities, there is a classification: N-type and P-type semiconductor. Now, the N-type semiconductor. What is meant by N-type semiconductor? So here, to get the N-type semiconductor, a pentavalent impurity atoms are added to pure semiconductor. if the pentavalent impurity is added to the pure form of semiconductor, n-type semiconductor is obtained. And the pentavalent impurity atom has 5 outermost electron, means the valency of the pentavalent impurity is equal to 5, rather than for silicon the valency is equal to 4. For germanium or silicon, the valency is equal to 4 and the pentavalent impurity has the valency is equal to 5. Means the size of the pentavalent impurity atoms is roughly same as the germanium and silicon. For example, we use phosphorus, strontium, arsenic like these pentavalent impurities. And as that amount of impurity is very small, that is for 10 power 6 to 10 power 10 atoms, there is one impurity. This is the amount of impurity is very small, and it is assumed that each impurity atom is surrounded by silicon atoms. So each impurity atom is surrounded by silicon atoms. For example, I am considering the phosphorus atom. So phosphorus atom has 5 valency electrons. So out of 5 valency electrons, the 4 valency electrons are required for covalent bond with 4 electrons of the silicon atoms. You can see the figure here. The center atom, the circled atom is the phosphorus and it is surrounded by the silicon atoms. So there are 5 valency electrons. So only 4 electrons are in bonding with the outermost electrons of the neighboring silicon atoms. Now there is 1/5 electron for phosphorus atom has no chance of forming the covalent bond. There is one more electron for phosphorus atom in the outermost orbit has no chance to form the covalent bond. So the 5th electron is much more easily detached from the parent atom. So this 5th electron is easily detached from the parent atom. Why? Because this is the free electron. There is no covalent bond. It is not forming the covalent bond. So as we adding the impurities, this phosphorus to the silicon atoms, one electron is free to move in the silicon crystal. So the 5th is much more easily detached from the parent atom, as we know, and very little amount of energy is required to detach this electron from the nucleus of its parent atom. As this electron, this 5th electron is in the outermost orbit, means it is very loosely bonding with the nucleus, and there is very less amount of energy is required to break the bond with the nucleus, means to detach the electron from the outermost orbit. Okay, so this energy is the energy required to detach the electron from the outermost orbit is 0.05 electron volts for silicon, and it is 0.01 electron volts for germanium. It is very small energy. So silicon atoms to 0.05 electron volts and 0.01 electron volts. Means suppose phosphorus is added to silicon crystal. So the 5th electron can be detached by giving the energy 0.05 electron volts. and if the same phosphorus atom is added to the germanium crystal, then to detach the fifth electron from the outermost orbit, it requires 0.01 electron volt. Now, each impurity atom donates one electron to the conduction band. Means by adding one impurity atom, there is one free electron. One free electron is generated. Means each impurity atom donates one electron to the conduction. So therefore, the pentavalent impurity is called donor type impurity. Pentavalent impurity is also called as donor type impurity. The large number of donated electrons, there are also some thermally generated electron hole pairs. They are thermally generated electron hole pairs. And the large number of electrons increases the rate of recombination of electrons with the holes. So, as in N-type semiconductor, the holes are the minority charge carriers and it has large number of immobile positive ions. Immobile positive ions means the electron is detached from the outermost orbit. There will be positive ion will be created. One electron is detached, so positive ions will be generated. So there are negatively charged electrons, positively charged holes, and positively charged immobile ions will be present in the N-type semiconductor. And electrons are majority charge carrier, whereas the holes are minority charge carriers. Now the P-type semiconductor. What is a P-type semiconductor? When trivalent impurity atoms are added to pure semiconductor, the P-type semiconductor is formed. Trivalent. What is a trivalent impurity? How many electrons will be present in the outermost orbit? So there are 3 electrons in the valency shell. So that's why it is called as trivalent impurity. So generally, the size of the trivalent atoms is roughly same as the silicon and germanium. And what are the trivalent impurities? Boron, aluminum, gallium and indium. The amount of impurity is very small. It is assumed that each impurity atom is surrounded by silicon atom. We know that concentration of the impurity means the doping rate, that is 10 power 6 to 10 power 10 atoms of silicon. There is one impurity atom of boron or aluminum or gallium or indium. So that's why these impurity atom automatically surrounded by the parent atoms, that is silicon atoms. So now the center, consider the trivalent impurity and it is surrounded by the silicon atoms, as you can see in this figure. So there are 3 valency electrons in the outermost orbit. So these 3 electrons form the 3 covalent bonds with the neighboring 3 electrons of silicon atoms. Whereas in the 4th covalent bond, there is a vacancy for the electron in the covalent bond. The doping atom has only 3 electrons in the outermost shell and the impurity atom is surrounded by silicon atoms, and these 3 electrons from the covalent bonds with the 3 neighboring silicon atoms. means there is a vacancy for the electron in the covalent bond. So the fourth silicon atom cannot make the covalent bond with the boron or indium atom. I am considering this atom, the center impurity atom, as indium. So there is no the parent atoms, that is the silicon atoms, cannot make any covalent bond with the indium atom, because indium atom does not have fourth valency electron. It has only 3 valency electrons. Means the fourth covalent bond is incomplete. Means there is only 1 electron. It is incomplete covalent bond. The vacancy that exists in the incomplete covalent bond constitute a hole. That is, the vacancy of electron or the absence of electron is called as hole. And the hole has tendency to complete the covalent bond from the neighboring atoms to complete covalent bond. The hole has the tendency to complete the covalent bond from the neighboring atoms to complete the covalent bond. An electron from neighboring atoms require some energy to jump into the vacancy. And when the electron from the neighboring atoms jump into the vacancy around the indium atom to complete the covalent bonds, the effect is twofold. So there large number of holes are created due to acceptor type impurity. Means for every adding of impurity atom, for one impurity atom there is one hole is generated. So therefore the large number of holes are created due to this acceptor type impurity. Means it is accepting the electron. So large number of holes increases the rate of recombination of holes with electrons, so that the number of electrons is further reduced than intrinsic level. The number of electrons is reduced than intrinsic level. In p-type semiconductor, holes are majority charge carriers and electrons are minority charge carriers. And here the p-type materials has holes as majority and electrons as minority charge carriers. There will be negative immobile ions. Negative immobile ions means it is accepting an electron to complete the covalent bond, right? So this is the always acceptor type impurity. So by giving the electron, the positive ion, negative ions will be created. So in p-type semiconductor, majority is holes, minority charge carriers are electrons, and there will be immobile negative ions also. They have two type of charge carriers and immobile negative ions. Now the effect of temperature on extrinsic semiconductor. The addition of small amount of energy means the addition of small amount of donor or acceptor impurity to generate the large number of charge carriers in any intrinsic semiconductor means donor. By giving the small amount of donor type impurities, there are large number of electrons and less number of holes are generated. And by adding the acceptor impurity, large number of holes and some less number of electrons are generated. Due to this large number of charge carriers, the conductivity of the extrinsic semiconductor is several times greater than the conductivity of the intrinsic semiconductor at the room temperature. As at the room temperature, only by breaking of the covalent bonds, some holes and electrons are formed, and due to that charge carriers, the current will be, the conductivity takes place and it is very less. And whereas it is zero, completely zero at the absolute temperature. But as the increasing the temperature of the intrinsic semiconductor, the conductivity is increasing. Whereas in the extrinsic semiconductor, at the room temperature itself, the conductivity is several times greater than the conductivity of the intrinsic semiconductor. All the donor atoms have already donated the free electrons. The additional thermal energy due to energy in the temperature only serves to increase the thermal produced charge carriers. So, as by giving the donor types or acceptor type atoms, there will be free electrons or free holes, and by the addition of thermal energy, means by increasing the temperature, so only it serves to increase the thermal produced carriers. The concentration of minority carriers increases due to thermal energy. Means by adding the donor atoms, electrons are generated. By adding the acceptor impurity, holes will be generated. But to increase the minority charge carriers population, so here the thermal energy is required. And when the temperature raised, number of covalent bonds will be quite large, broken, and the number of holes is nearby equal to number of electrons. Now the extrinsic semiconductors acts like an intrinsic semiconductor with higher conductivity. The extrinsic semiconductor acts like intrinsic semiconductor with higher conductivity. So this is the effect of temperature on extrinsic semiconductor. So in this session, we discussed about the intrinsic semiconductor and extrinsic semiconductor. So the pure form of the semiconductor is called the intrinsic semiconductor, and we know that the semiconductor properties of semiconductor lies between insulators and the conductors, and the resistance decreases with the increase of the temperature, and the conductivity increases with the increase the temperature. So like this, there are classification of the semiconductors: elementary semiconductors and compound semiconductor, and it may be classified into another two types based on the type of the impurity atom added, that is extrinsic and intrinsic semiconductor. So in the intrinsic semiconductor, it is a pure form, and it is the very low temperature, means it is 0 Kelvin. It acts like an insulator, and by giving the means the electrons are tightly bound to the nucleus, no free electron is present, the conductivity is very very less and is equal to 0. But as the temperature increases, the covalent bonds will be breaked and some electron hole pairs will be generated. So due to that electrons and holes, conductivity takes place. Now, how the electron hole pair is generated? So as the temperature increases, some covalent bonds will be breaked and the electrons are very free to detach from the nucleus, from the atom. Then there is a vacancy called as the hole. The vacancy of electron is called hole. So in this intrinsic semiconductor, the conductivity, the number of holes is equal to number of electrons, and the conductivity is due to the movement of electrons as well as holes. And it is negative, electrons are negatively charged, the holes are positively charged carriers. So what is the energy to break the bond? So it is 0.72 electron volts and it is 1.12 electron volts, and this energy is also be called as the energy required to lift the electron from the valence band to conduction band. It's also 1.12 for silicon, 0.72 for electron volt for germanium. Now the effect of temperature on intrinsic semiconductor. So as the temperature increases, the conductivity increases, and as the temperature increases, the resistivity decreases. So negative temperature coefficient of resistance. And there is a classification of extrinsic semiconductor. At room temperature is the conductivity is very low for a pure form, and by adding some impurities, so we can increase the conductivity, and this process is called the doping. And the doping rate is 1 impurity atom per 10 power 6 or 10 power 10 atoms, parent atoms. And n-type p-type semiconductor, or the n-type semiconductor is 1 pentavalent impurity is added to the pure form. N-type semiconductor is formed, and we generally use phosphorus, strontium, arsenic for p-type semiconductor. And the phosphorus atom has 5 valence electrons. Only 4 of the 4 valence electrons are required for covalent bond, and the 5th electron is very free to move, and it is easily detached from the nucleus, and this energy is equal to 0.05 electron volts for silicon and 0.01 electron volts for germanium. And large number of donated atoms are added, so the large number of electron holes pair will be generated. So holes are minority and electrons are majority charge carriers, and there will be immobile positive ions in the n-type semiconductor. Whereas p-type semiconductor, trivalent impurities are added to the pure form, and generally the trivalent impurities are aluminum, boron and gallium. And here only 3 doping atoms, 3 valence electrons are here to form the covalent bond with the neighboring silicon atoms. So the fourth covalent bond is incomplete with the electron, and this absence of electron is called hole. So here the hole is always accept 1 electron, so that's why it is called as acceptor impurity. So the hole has a tendency to complete the covalent bond for the neighboring atoms to complete the covalent bond. So here when the electron from the neighboring atoms jump into the vacancy atom, that is to complete the covalent bond. So in the p-type semiconductor, majority charge carriers are holes and minority charge carriers are electrons, and there is negative immobile ions in the p-type semiconductor. And holes are majority and electrons are minority charge carriers. And the effect of temperature on extrinsic semiconductor is, as temperature increases, the covalent bonds will be breaked and large number of electron holes pair will be generated. So the extrinsic semiconductor now acts like an intrinsic semiconductor with higher conductivity. So here in the extrinsic semiconductor, the charge carriers are generated through by adding the impurities atoms as well as by thermal energy. So this completes my session. Thank you one and all.